This problem consists of an insulating solid sphere of radius a. Why does it matter that it's insulating? It just means that the charge is fixed in place. It's not allowed to flow because it's an insulator. And it's a uniform volume charge density rho and carries a total charge positive q. So what is rho? Rho is the charge density, which is the total charge q over some volume. And we'll also note that this is the volume of this sphere of radius a. So the charge density equals q over 4/3 pi a cubed, volume of a cube. We'll use that later. So remember, volume charge density is just like mass density. It's, we would use even the same letter. The mass density rho is mass per unit volume. This is the charge density rho, so it's the charge per unit volume on that object. So the question asks us to find the electric field for R less than A and R greater than A. So inside of the charged insulating sphere and outside the charged insulating sphere. Let me just sketch that real quick. So the sphere has charge q and radius a, and we want to find for r less than a and for r greater than a. So let's start for r greater than a. I'll do that right here. Okay. I'm going to draw a Gaussian surface, a Gaussian shell that matches the symmetry of this shell, of this charged sphere. And why do I do that? Because I know if this is charged, the electric field is going to point radially outward everywhere, just like it would a point charge. But I also know that this Gaussian surface, which again is an imaginary surface that we do just for this purposes of using Gauss's law, it's going to consist of infinitesimally small area elements, dA, and they are all oriented perpendicularly, pointing away from that Gaussian surface that we drew. So at every point, dA is, I don't know if it's appropriate to use the word tangential for a three-dimensional object. I think maybe it is. But I'm sorry, this isn't tangential anyways. It's the opposite of tangential. This is perpendicular, normal to the surface. But what we note is that E is always parallel to dA. So let's go to Gauss's law. The flux through our Gaussian surface is defined by, this is the definition of flux here, E dot dA, and the rest of Gauss's law says that equals charge enclosed over epsilon naught. Well, since we said E is always perpendicular to A, well, we don't need that dot product anymore because, well, this would just be E dA cosine of theta, the magnitude of E times the magnitude of dA times the cosine of the angle between it. I'll even put E A down there. But this angle is always 0 degrees. They are always parallel to each other. We define our surface so we can do that. We wouldn't define a surface in which dA was not parallel with E. So this is just E dA, which is the same as saying, well, I have to take one more step back. What's the relationship of E to dA? Well, we also know because of the symmetry that the electric field is the same at all points along this Gaussian surface because it is the same distance away from this spherical charge. We're treating the spherical charge like it were a point charge. The radius, if the radius is fixed, then the electric field is fixed, and you can pull it out of the integral, which means this just equals E times A. I may give you a test question where I say, explain how you go from here to here. Something to know. So EA is equal to charge enclosed over epsilon naught. Now, just like this is the flux through the Gaussian surface, I have to remind you that this is the area of the Gaussian surface. Area of the Gaussian surface. So we know what that is. E is just equal to 4 pi r squared. The area of a sphere of radius r. And the charge enclosed, well, it contains all that charge. So the charge enclosed is just capital Q over epsilon naught. So E equals 1 over 4 pi epsilon naught Q over r squared, which is just the definition of electric field for a point charge. Or it equals K Q over r squared. Okay, so now let's go on to the more interesting part, which is the electric field inside. Separate here. I'll make also my charged sphere a little bit bigger. Remember radius A, and we are going to make a Gaussian surface of radius r that is inside the sphere. Remember, it's a three-dimensional sphere, and I'm just drawing a two-dimensional slice or two-dimensional projection of it. Okay, so back to Gauss's law. The flux through our new Gaussian surface is equal to the integral of E dot dA equals charge enclosed over epsilon naught. Now, just like this situation here, the electric field from the charge enclosed by the Gaussian surface is always going to point radially away, as will dA. So, and the electric field is the same at every point along the outside of this Gaussian surface as long as we're at fixed radius. So this is just equal to EA equals Q enclosed over epsilon naught. Now this is where it's important that you remember that this is the area of the Gaussian surface. So E times 4 pi r squared is equal to Q enclosed over epsilon naught. But now this is where things get a little bit tricky, because before, when we were outside of the sphere, we enclosed all of the charge. But now, because the charge is uniformly distributed throughout this insulator, and because it's an insulator, so electrons can't flow around in it, then we are only enclosing a portion of that charge. So how do I describe the portion of charge that I'm including? Let me draw a line here and say Q enclosed is equal to the charge density times the volume of the Gaussian surface. So this is the volume of my Gaussian surface. Multiply that times the charge density, and I have the total charge enclosed. So what is the charge density? Well, we can substitute in for that. Q over 4/4 pi A cubed. Remember, this is the total charge of the whole sphere divided by the total volume of the whole sphere. You have to use those terms because that's the only way to get the density. And then we will multiply that times the volume of the Gaussian surface, which is 4/3 pi r cubed, because this is only the radius of the Gaussian surface that we draw, and we have to define the density as the total charge divided by the total volume using the total radius A. Well, a lot of stuff cancels out. The 4/3, the pi, so I'm left with Q r cubed over A cubed. Now I can put that back in over here. So I'll say the electric field is equal to 1 over 4 pi r squared. I just moved that over to the other side. Times now the charge enclosed, I'll actually do 1 times epsilon naught just to move that out, times the charge enclosed, which is Q r cubed over A cubed. So these two r's cancel, one of those cancel, so the electric field is equal to 1 over 4 pi epsilon naught, that is just K, the Coulomb constant, times R over A cubed. Or another way of writing that, I can say that the electric field as a function of R is equal to K Q over A cubed, these are all constants, times R. So for radius less than A, E is proportional to 1 over R squared, and for R is greater than A, E is proportional to R. So if we were to look at changing R in the electric field, it would look something like that, where this is R equals A. The charge enclosed, and therefore the electric field, increases linearly as you get to the outer surface of this charged sphere, and then it drops off with 1 over R squared. So all of the charge that exists around the Gaussian surface when you're inside of that sphere, all of that does not, none of it contributes to the electric field. It all cancels out.